Yeah, sorry for the delay. So yes, this is about graph neural networks for FPGAs. It's a it's a work done with my local collaborators at CERN and also with the HLS4ML authors. HLS4ML I'll explain in the talk. So I will talk about challenges in implementing graph neural networks, algorithms, as FPGA firmwares, and also discuss methods to overcome those challenges using our experience with the particular architecture as an example. Okay, so let's get started. So first, just to be on the absolutely same page, let me give a quick introduction of graph neural network. Obviously, most of you or all of you maybe are very familiar with this already, but graph neural network is a neural network on sets of vertices and edges that connect these vertices. Input to the neural graph GNN would be the vertices and edges with intrinsic features, and output comes out the vertex or edge labels or global properties of the graph, or just properties of the various vertices as well. So the cartoon in the middle illustrates what I just said. You have vertices and edges, and U would be sort of the global property of the attribute of the graph, and each of these has features typically as like feature vectors. And out of that, for example, the examples on the right, the first example is a network where you feed in points from like a point cloud, and the network can do labeling of individual points, saying okay, this point corresponds to the wing of the airplane, and this point is the fuselage, etc. The second example would be you feed in these chemical compounds expressed as graphs, and out comes the sort of toxicity or other global properties of these compounds. So those are the things that you can do with graph neural network. Now, interesting properties of graph represented data are that the list of vertices is variable length and unordered. So it's like very set of vertices, and also that the edges can encode not just topology. Edges connections would be basically topology itself, but it can also encode geometry as distance in the features, represented as feature, some number in the features. So graph neural network is a very natural tool for machine learning over sparse data that can be sort of expressed as points that have relations, distance between them, or etc. Like sets of points sampled in space, basically, which high energy physics detector hits are. So that's how we sort of look into this. But before talking about high energy physics, I'd like to quickly introduce another concept, which is the graph network, because it will be helpful in understanding the neural network architectures that appear in this talk. So graph network was formulated in this 2018 paper by Battaglia and company. And basically, it's a network built from graph to graph feature transformation blocks. The block is represented in this cartoon in the middle. In this cartoon, the circled phi's are typically they are multi-layer perceptrons, the transformations. And each block consists of 3 parts. One is the computation per edge, so it basically involves a loop over edges. But it's a transformation over edges, and then there's the second block which takes the input from the first. That's the computation per node, the node block, and then finally you have the aggregate computation that sort of takes all these input and computes the global property of the graph. Now, if you omit certain connections or operations in this diagram, you end up with variations of graph network, and many graph neural network algorithms can actually be understood as these variations. And algorithm that I'm going to talk about can also be understood this way. Now, coming back to high energy physics. So graph neural network has been a hot topic in the field, as evidenced by the number of talks. Two talks before it was also about graph. Number of talks just in this conference, right? And I think the reason that it's hot is that GNNs provide a unified basis to think about different tasks in high energy physics. And what I mean by that is tracking and clustering. They're both pattern recognition on sparse data. And this is more so with next generation high granularity 3D calorimeters such as CMS-HGCal for high luminosity phase. So in this sort of view, there's a translation of high energy physics hits can be translated into vertices of the graphs. And tracking and clustering then essentially becomes just prediction of correct edges that connect these vertices, and using, you know, given vertex features such as XYZ or time or energy or whatever. And then, you know, things you do on these tracks and clusters, such as, you know, particle identification or energy regression, these are just prediction of global graph features given a connected graph. And if you formulate it this way, it's basically detector agnostic, right? I didn't use like, oh, this is a crystal or this is silicon, etc. I just said X, Y, Z, T, and E. So a good base algorithm can be used for all tasks. That's the claim here. And this sort of usefulness of the graph neural network has already been well proven in event reconstruction for LHC and neutrino experiments. You know, these talks, I think, talk about those. But these are sort of mostly offline tasks where you can, you know, spend some time, like a couple of seconds even, to do really complex stuff. But what I find interesting would be, as a next front, is to do this on fast, you know, like a fast environment, basically level 1 trigger. So basically, can we put graph neural network as firmware on FPGA is the question. Now, when I say fast, right? Okay, or when we talk about level 1 application, there are some general requirements, and the first and foremost is that it has to be fast. And when I say fast, I mean less than 1 microsecond, basically. And that's you know, in stark contrast to offline. As I said, it would be like, you know, using a couple seconds even, or in HLT you can use maybe like up to 1 millisecond or so. But for LNT, the total latency you have as the level 1 system is 12.5 microseconds for a CMS. So if you're talking about local reconstruction, that's really just a small, tiny part of this total system. This thing has to run in less than a microsecond. Another important, sort of equally important point is that it has to be high throughput, because events at level 1 sees events at 40 megahertz in LHC, right? So as a system, it has to accept every event every 25 nanoseconds. Of course, in practice, you time multiplex the system, meaning you have copies of the same system that sort of has distributed event, you know, like one event coming into one copy, and then another event coming to another copy. And time multiplexing usually is order 10. So individual components may accept one event per 250 nanoseconds. But then if your algorithm is maybe like a processes, you know, like one track at a time or one cluster at a time, then you, again, the throughput has to be much, much higher than that. So high throughput. And then finally, the algorithm has to be small because it has to fit on one FPGA chip. So having those requirements in mind, the challenges on putting graph neural network on FPGA is, first, the sheer number of operations that are involved. Because for realistic problems, you would have, you know, like thousands or tens of thousands of vertices and edges that connects them. So 10 to the 4th, 5th, or even higher. And as I said, the transformations in these graph network blocks are multi-layer perceptrons, meaning they involve dense matrix multiplications. So, for example, there's the XTrackX GNN segment classifier model in the paper at the top, which, to be fair, is not optimized for resource usage. But anyway, there's one calculation showed that there are order 10 to the 6th multiplications per vertex in this model, and order 10 to the 7th per edge. And so if you have, you know, multiple graph modules, these are the graph network blocks that I mentioned, you end up with 10 to the 10th multiplications. That model like that cannot fit on a FPGA without reducing the number of vertices, like just making the input smaller or compressing the model a lot to use much fewer multiplications. So that's one challenge. The next challenge is that lots of graph neural network algorithms use substantial memory, like gigabytes or tens of gigabytes. But FPGA on chip RAM is typically order 10 to 100 megabits. So you'd need an implementation of these GNNs that drastically cuts the memory footprint. And then finally, it's a subtle point but very important, is that when you feed a list of edges to a network, you're essentially making a sparse representation of the adjacency matrix. Because what I mean is you're also feeding a list of vertices, right, to the network. So list of vertices, list of edges, and these list of edges, the edges will make dynamic references to the this array of vertices. Like I want to use vertex number 0 and number 13, for example. But FPGA logic doesn't really like that. They like to have a known access pattern already at the synthesis time. So this type of irregular memory access becomes a problem. So those are the challenges. So with those challenges in mind, we picked a specific GNN algorithm to see if it can be implemented as an FPGA firmware. The algorithm is called GarNet, and it's introduced in the paper at the top right. It's a general purpose graph network, which was already actually designed with level 1 usage in mind. And the particular features that make it a good candidate for GNN and FPGA are that one, it doesn't use edges. It doesn't have the edges and input. So directly that leads to small memory footprint, and also it cuts out this dynamic access issue that I just mentioned in the previous slide. And then also another feature is that vertex features are weighted by a nonlinear function within this graph network block of GarNet. And with this, it can learn non-trivial features with very shallow transformation networks. So the MLPs, the multi-layer perceptrons, these so-called PHYs, can be rather small. And that means it requires small number of operations. So, but then, even though it was designed to be lightweight, there was no actual firmware implementation. The original implementation is in TensorFlow and Keras. So we picked this network, and as I said, we picked this network and studied how to put it on FPGA in detail. Okay, so jumping on a bit, basically, in the end, we had to make some modifications to GarNet. And in order to understand what we did, I'd like to explain the original algorithm in a little detail. So this is the GarNet block diagram, where you have the list of vertices with features coming in from the left, and same vertices with updated features going to the right. And there's the internal operations, but no edge block, as I said, because there's no edge provided. Okay, so first there's the encoder that transforms the vertex features into an internal representation. And then the same set of input features are also used to calculate another set of numbers, which are quote-unquote distances to aggregator nodes. The aggregators are virtual nodes that communicate with all vertices. And in this third step, basically these encoded features from phi in are sent to these aggregators, but with weights that are given by the Gaussian of the distance and nonlinearity part. The aggregators computes the mean and max of all these the features that are sent from the vertices, and then send them back to the vertex with another application of the same weights. And then finally, there's the decoder that computes the output features for each vertex. And then this block can be repeated multiple times to create a deep network. But yeah, that's just one unit. Okay, so and then before going into the actual meat of the talk, we also need to talk about another set of background knowledge, which is the key concepts in FPGA logic design. So obviously, okay, sorry, there are there are resources on FPGAs that are sort of primarily divided into 4 categories, I guess. One is the lookup tables that perform logic operations like OR and AND. And then there's the digital signal processing units, the DSPs, which essentially used for multiplications. And then there are flip-flops and memories. Both are storage, but different technologies, obviously. And so there are only finite numbers of those components, obviously. So we need to understand how much of each are used for the design logic. So that's something you need to be paying attention to. And then there are 2 concepts that are sort of important in understanding how FPGAs can be advantageous compared to other processors. One is the parallelization, the other is pipelining. So parallelization means that you can unroll the loops as much as you want, given the resource usage constraint. And each unrolled loop body executes in an independent circuit. So the cartoon at the bottom represents how a serial loop looks versus unrolled loop looks like. So in the serial loop, you would require 9 clock cycles to process these 9 stages, 3 stages and 3 events or whatever. But in the unrolled loop, you only need 3 cycles, but use 3 times as much resource. Right, so it saves execution time, but costs resources. Pipelining is a different way of sort of overlaying these operations. Basically, what it is you start processing the next input before the current one is processed. So just using the same example, you have 3-step processing, but after the first blue event, stage 1 is complete, you can already start the stage 1 of the orange. And important thing to note is that there's no, stage 1 only executes 1 at a time, 1 at each cycle. So you don't have to clone the circuit. There's no copy of resources. So pipeline doesn't necessarily cost resources to do. But you need to sort of have a good implementation of the circuit to be able to do this. And then one keyword is the initiation interval, which is basically just the time before the next input is accepted. So given those, the key metrics in FPGA logic design is the latency, how long your algorithm takes to execute, and that depends on the number of serial operations. And then there's the initiation interval that I just mentioned. So yeah, this mostly depends on the implementation, and in particular, you want to simplify the data flow to shorten the AI. And then finally, there's the resource usage that I already mentioned in the first part of the slide, previous slide. Okay. One thing to note is that here's the DSP tends to be the bottleneck. So the multiplications are the most scarce resource often in FPGA. Okay, so those rather complicated sort of balance between different metrics can be sort of made easier for physicists by this package called HLS4ML. It's a package for machine learning inference on FPGAs. And what it is it translates the machine learning models in Keras or PyTorch, whatever, into high-level synthesis projects. High-level synthesis is sort of the framework where you can translate C++ code into FPGA firmware. Then this translation actually is done by the Xilinx proprietary software called Vivado HLS. But HLS4ML basically just constructs this project. And the core asset of HLS4ML is that is the original library of these HLS templates. So those templates implement the machine learning algorithm layers, such as dense or convolutional network, etc. And basically, the HLS4ML just puts these together and creates a project. The features of HLS4ML, I think I should skip this actually, but yeah. Okay, well, one thing I should mention is that you can do weight quantization at the third bullet. What it is it represents weights by -1 or 1 or -101 ternary network. Instead of having a full floating point or fixed point precision numbers as weights. So it drastically reduces the operations, multiplications in the network. And final point is the project uses fixed point numbers usually, not the floating point, because FPGA executes much faster with fixed points. Okay, so the modifications that have been done to GarNet to fit it on FPGA. And this was implemented in HLS4ML framework, is that first we parallelized the block, so you have copies of this GN block for different vertices. But obviously, you can't have thousands of copies of these rather complicated GN blocks. It'll cost too much resource. So there's the reuse, which basically is the time loop. And this reuse factor, the length of loop, is configurable. So users can choose between the resource usage and latency, as always. And then there's the shortcuts that were in the original implementation. But to simplify the data flow so that we can do pipelining, these shortcuts, data feeding was eliminated. And then the encoder and decoder can be ternarized, meaning can use ternary networks. It can still be a full precision network as well, but there's an option to use a ternary network, and that reduces multiplications. And then the Gaussian weights are not computed per sample, but just are pre-computed and stored in the lookup table. And then finally, aggregation is only done for mean, not max, and that reduces operations as well. So those are the modifications. And then also stacking was optimized. So as I said, the GarNet layers can be stacked, but typically you would stack these layers, and then the output of the final layer is reduced over vertices. So you can already build in those into just stacked GarNet layer as a single layer. So basically, you have the vertex output of one layer directly fed into a vertex input of the next layer without creating an array of vertices in the middle, and that reduces the memory usage and also the latency. Okay, so those are sort of tricks that we did to put GarNet on FPGA, and I think some of those can be generalized when you think about putting GNNs on FPGAs. So that's sort of the take home here. But just as a case study, to see whether this actually works, we applied this network onto a toy calorimeter simulation. So the geometry of the calorimeter is cut out of a high granularity 3D calorimeter with like 50 layers and some fine segmentations in X, Y, Y. And as a physics process, we just shoot electrons and pions and a lot of pileup pions and photons on top of them. The pileup energy in flux represents HLHC type environment. And so the sample of these events, from these events, is the cluster around the highest energy hit. But cluster is just a cylinder around the highest energy hit, because that's the sort of clustering that can be done. I'm seeing some message. Sorry,
I was trying to warn you that you're about 5 minutes.
Right. How many? Sorry.
About 5.
5 minutes. Okay.
I wrote 4. Yeah.
Yeah. I thought I only had like a minute or two. Yeah. So that's the sort of clustering that can be done in a level 1 environment. So very simple one. And then each hit is fed as a graph vertex and only has 4 features: X, Y, Z, and the energy. So we created 250,000 electron events and 250,000 pion events, and the task is to identify this primary particle out of these pileup overlaid, and also do energy prediction at the same time. Here's the model. You have the GarNets, 3 GarNet layers stacked together that end up with the mean of the vertices, and then that's fed to some couple of dense layers, and then from that you branch off to the energy prediction branch, and also the particle ID branch. So loss functions, right? I don't need to explain those, but the important thing is that 2 versions of this model was created and trained separately. First one is labeled a continuous model, which is where encoder and decoder weights are in full precision fixed point numbers with rather wide representation. And then there's the quantized version where encoder and decoder are ternarized. So all the weights in encoder and decoder are just 1, -1, or 0. So how did these perform? So for classification performance, here's the ROC curve. So the y-axis is the electron ID efficiency. The x-axis is the pion rejection efficiency. So 1- false positive rate. We're comparing 4 models: Kehr's implementation of this modified GarNet for continuous and quantized, and HLS version of those. Kehr's version uses floating point. That's the essential difference between the HLS version. Floating point tend to be more accurate. So if you look at the 4 curves, though, they basically overlap. If you look at the zoom in, you can see that Kehr's continuous performs the best, and Kehr's quantized, HLS quantized actually perform very similar, because once you're quantizing the weights, floating point, fixed point doesn't really matter. So these there's a small difference, but the order is as expected, and that was pretty cool. And then there's the reference curve also in this plot that doesn't perform as well as this GarNet-based model. In terms of regression, plotting here the response, that's the energy predicted over energy truth at the median and spread of the this response in 10 GeV bins. And basically there's, again, negligible difference between the Keras version and HLS version for both continuous and quantized models. The result isn't production grade per se, but it does show that GarNet can do regression as well, not just PID. And I would note that there's lots of room for improving the model itself or loss function to do, if you're serious about doing regression. And then there's also the reference that it doesn't perform as well. So this was all about clustering and calorimetry and this tracking conference. So is this relevant, right? And so the question is, can we FPGA size GNN infer edge and vertex properties, so the local properties, and therefore do tracking? One thing to note is that the GarNet is a largely vertex local algorithm. So we were doing global inference, right? Global PID or energy, but this must be happening through inherent local inference. And to sort of qualitatively confirm this claim, we looked at how the energy prediction changes as you sort of perturb individual hit energy. And basically, if pilot projection is perfect, you would have zero effect on the global energy from a perturbation of the pileup energy, and one-to-one change in the global energy when you change the primary energy. And you can see that it's not as exact as that, but still, at the top is the primary fraction shown as blue to red. So that's the fraction of energy and hit energy from the primary particle, and the bottom is this the rate of change of this primary predicted energy from perturbation, and green and red do overlap between the two plots. So the network is assigning higher importance to hits from primary particle, meaning it is inferring local information at hit level. So that's the sort of relevance to tracking. Anyway, so those were the physics performance. Synthesis, actual, did we use up resource, or can this actually fit in an FPGA? The conclusion is that it does fit in FPGA, and also the latency is sub-microsecond, so we cleared that goal as well. But this can't be, again, in production yet, because the initiation interval is a little too long for level 1 trigger. Okay, so coming to conclusion, graph neural networks show promising performance in high energy physics tasks. So we wanted a new implementation for firmware triggers. So in this talk, I identified key challenges for GNNs on FPGAs, which are the number of operations and also the memory capacity and access, the way of accessing. I also presented GarNet, which addresses these issues. So by not having vertex-to-vertex edges, and also having nonlinearity in edge weights to reduce multiplications. And this will be integrated into HLSM for ML very soon. So that means there's a general purpose graph neural network layer on FPGA that's available to public readily. I also discussed algorithm simplifications and optimizations to fit a GNN in FPGA. And finally, we demonstrated a sub-microsecond latency GNN circuit for a level 1T like physics task. That's all. Thank you.
Great. Thank you. Is there an urgent question or two? Yeah, Daniel.
Yeah, sorry, if you said this, I must have missed it, but is there a hit to your accuracy, or have you looked at whether the hit to your accuracy from removing this, to optimizing with this shortcut that removes the input to the node features from the encoded space?
So it's a good question. The shortcuts were introduced because it gave higher accuracy in the task that was in the original paper where this layer was sort of introduced. So I did not check for this case study task, but I'd expect that there is some accuracy that you can buy. But because the task is simple and the input is not as dense as it's a trigger level study, I'd expect the difference to be small.
Okay, interesting.
Anyone else? Tara, I just had a question. If you remove the 1 microsecond constraint, do you gain a lot of freedom in your perspective for more complicated graph neural networks on fitting into FPGAs?
I believe so, but you would still need to limit the number of multiplications because there are only finite number of DSPs. So yeah, but yeah, okay. So you can yeah, if you don't have the time constraint, you can reuse as much as you want the same multiplications. So yes, I think that'll buy you a lot in terms of complexity.
Okay, thank you. Okay, should move on. Then where's my timetable? Thanks again, Yutaro.